gentlemen, welcome to the late morning show with Mr. Bull, and today we have an incredible guest with us that I am excited to introduce to you this morning, late morning. So without any further ado, let's welcome into the room Mr. Bull. Oh, Mr. Bill, we are so thankful that you have taken time out of your busy schedule to talk to us about your YouTube channel and how you're getting on in lockdown. So I guess my first question, let's just dive right into this, is how are you getting on in lockdown at the moment? Oh, Mr. Bill, thanks for having me on the late show. I really appreciate it. Do you know what? Great question. Lockdown is pretty hard. I mean, I'm going a little bit crazy, I think. I'm seeing double of myself sometimes, but do you know what, sometimes that's where the inspiration comes from, and I'm just so stoked to be here chatting with you and chatting to all of you guys at home who have been tuning in for such a long time now. So yeah, thanks Mr. Bill. Oh, Mr. Bill, that's brilliant, thank you. Now another wee question I have for you. You last March had about 60 subscribers. How on earth did you manage to get 265 subscribers as of yesterday? What a feat, first of all, but how did you do that? Mr. Bull, that's a fantastic question. Do you know what? I was down in the ashes, and out of nowhere, people seem to like the channel. The fans seem to like the channel, and I'm now sitting on 265 subscribers. I don't know how it happened, but I just want to say a huge thank you to all those fans out there. But I do think I know one of the reasons why, and it's this wee girl here. I thought I'd bring her onto the show. Let's lift her up. Oh, there she is. Nova, say hello. Oh, what a beautiful girl. What a beautiful girl. So I think most of my fandom is down to her, so I can't take most of the accolades for this. It's definitely the fans and Nova. Oh, Mr. Boo, you're an inspiration to me, so I just want to say thank you for that. Now, we're moving into 2021. What would you say is your hope for 2021? What am I hoping for 2021? Oh man, that's a tough one. That is a tough one. But do you know what I hope for? I hope for everyone who watches this, who is sitting a National 5 exam, either now, this year, or in the years to come, to get an A if they watch me every single day. That's what I hope. So if you're listening, I hope an A for you in National 5 Physics. That's what I hope for. That's my hope for 2021. That's my hope. Mr. Bill, thank you so much for your time. As we said, it is precious at the moment, I understand that. But just for all the viewers at home, what is your lesson going to be on today? Oh, do you know what? I'm excited for this lesson. We are moving on to radiation. Radiation part 1, not 2, 1. So Mr. Bill, no, thank you for asking. I'm really excited to start radiation. It's been a long time since these guys have done it. I'm not entirely sure how good they are at it, so we're going to try our best and let's hope that it's all good. So yeah, that's my plan. Well, there we have it, folks. That's all for today on the late morning show with Mr. Bull, and we do not want to take any more time away from your studies, so I'm going to get back to whatever you're doing with Mr. Bull in 3, 2, 1, and go. Okay, a little bit of fun there, National 5, but now we're going back into the prelim revision. And this time we're looking at radiation. So subscribe, like and share, you know the drill. Constant message in an unprecedented time. Unit 1, radiation. Okay, so we've not done this for a long time. So you might be just racking your brains about what radiation even is. I'm going to talk to you about the first half of the radiation course, and next week we'll do the second half. So what is in today's work? We will be covering ionization, activity, absorbed dose, and equivalent dose. Okay, with all the questions in your past paper questions based on this stuff here. Okay, now let's talk about ionization. Firstly, what is an atom? Now, for those who do chemistry, this is very, very easy. You have a nucleus. In the nucleus, you have a proton and a neutron, and you have electrons
that orbit that nucleus. Okay, protons have a positive charge, electrons have a negative charge, and neutrons have no charge. Okay? Now, what are these radiations made up of? Well, we have 3 different radiations: alpha, beta, and gamma. Okay, remember alpha is a helium nuclei, so just the nucleus, which has 2 protons and 2 neutrons. Then we have a beta, which is just a fast-moving electron. And then we have gamma, which is, as you should know, is just an EM wave, okay, an electromagnetic wave. Now, an unstable nuclei is a nucleus that wants to break apart and become smaller, more stable, often releasing radiation when it does so, okay? And this is basically the form of all radiation. It's just big particles being broken down into smaller particles, okay? And as you can see here, radioactive atom gives off some energy in the form of radiation, and it gives off a particle. Alright, it wants to get stable, that's why they do it. So what is ionization? Well, ionization is when electrons are removed or added from atoms to give charged ions, okay? Now, you should all know the definition of ionization. It's one of the key things you must know. It's the adding or removing of an electron, okay? Please know that definition. It's very, very important. And the ionization becomes one of the ions as a result of an electron being added or removed, becomes an ion. An ion is this fancy word for basically an atom that has gained or lost an electron. Okay, it's become an ion of that atom. Okay, so it's the addition or removal of an electron. So therefore it becomes ion, and therefore ionization. All right, so ionizing radiation, there's obviously you have the 3 types of radiation, and they have different forms of ionization. Okay, alpha particles are helium nuclei, they contain 2 protons, as I said. Beta is a fast-moving electron, and gamma is a short wavelength radiation from the EM spectrum. Okay, so they ionize in different ways, and they do that based on their structure. Okay, now you should also know how much of these radiations are absorbed by different materials and thicknesses. So for example, if I was to play this, which I can't because it's on Google Drive, but if I was to play this, alpha cannot go through paper. So therefore it can't go through aluminium and it can't go through lead. Beta can go through paper, but cannot go through aluminium, and therefore cannot go through lead. Gamma, on the other hand, can go through paper, can go through aluminium, and some parts can get through lead, but on the most part it doesn't go through lead. Okay, so please make sure you remember the different parts, the different absorptions of alpha, beta, and gamma. Now, absorption and penetration. We know that alpha has a range of also just centimeters, okay, and it is absorbed by a sheet of paper, and it's the least penetrating radiation. All right, it's the least penetrating. Beta, on the other hand, has a range of about a couple of meters, and is absorbed by a sheet of aluminium, as I've just said. And gamma has a range of kilometers, okay, and it is absorbed by thick pieces of lead. And it is the most penetrating radiation. It's the reason why we use that one the most for medical professions. Okay? So, ionizing effect. Alpha has the highest ionizing effect, beta has the lowest ionizing effect, and gamma has a low ionizing effect. Sorry, beta and gamma have a low ionizing effect. Okay? Now that's very similar to the weighting factor that we're going to come and chat about very soon. Okay, so that's ionizing effect. Now, this is a very good graph or table that kind of sums all that up. So pause it, have a look at it, see if you can understand it. You have one of these in your booklets. So, yeah, have a look at it. Make sure that you understand every single part of this table, because this is a great summary that will help you answer any question that comes up in the National 5 exam. Okay? Now, how do we use this radiation? Well, we use a lot of it in the medical profession. Radiotherapy is when radiation is used to kill or alter cancerous cells. Very expensive equipment, but very groundbreaking, and actually can reduce cancer and tumours by just targeting it with gamma radiation, intense gamma radiation. And it's why people will often get hair loss and things, because they're obviously being irradiated with radiation. So not the most pleasant experiences, but a very effective way of reducing tumours. Also used for sterilising instruments. Okay, we can use gamma radiation to sterilise in medical instruments to make them clean. If we don't have a spare gamma radiation gun, we can also just sterilise equipment with a match or something like that, or with fire. But gamma radiation is used in the medical profession to clean and sterilise instruments for use. We also can use it for tracers. Now, tracers are quite important. A radioactive tracer is injected into a patient, and normally this will be a gamma source as it needs to pass through, because remember it's the most penetrating. And the gamma camera is used to track the source's progress around the body, allowing doctors to diagnose various illnesses. For example, what happens if the source gets stuck somewhere? Then that means there must be a blockage, and then they can fix that. Same idea with industrial wise, they can put a gamma tracer in a pipe system, and if there's a blockage, they will know that because it will be emitting it from the same point. Okay, so it's actually very, very useful using tracers, but we need to use gamma because it's the most penetrating. Okay. Now, let's talk about activity. There's 3 equations, and this is kind of all talked about as dissymmetry. But activity is the number of nuclei decaying every second. So, for example, if we had 20 atoms decaying in 1 second, you would say that the activity was 20 becquerels. Okay, BQ, it stands for becquerels. And the equation is A equals N over T. Now, again, you should be very, very good at 3-letter equations by now. Okay, A equals N over T. Make sure you remember that. It's in your data sheet as well, so you don't really need to remember it, but I'm sure by this point you will have all these in your head. Okay, now N has not got a unit. It's just the number of decays, but A and T do. Okay, so number 3, absorbed dose. We're rattling through this. Absorbed dose is basically the energy absorbed per unit mass of the absorbing material. Okay, so basically if you're the tumour, you will receive an absorbed dose because you will receive some sort of energy for the mass that you are as a tumour. Okay, so the higher amount of radiation energy being transferred to the body means a greater risk of damage. So obviously a higher absorbed dose would be very damaging to an individual. So absorbed dose is measured in grays, and that's at capital G and small y. The equation is D equals E over M. Okay, so D is absorbed dose, equals E, which is energy, divided by M, which is mass. Okay, D is in grays, energy is in joules, and mass is in kilograms. Okay, now that then moves on to equivalent dose. And equivalent dose, before we go any further, we need to talk about a weighting factor. Now, we talked about ionizing effect just moments prior to this. So what is the weighting factor? Well, the weighting factor is how each radiation has a different effect on biological tissue. Okay, so the more dangerous the radiation to tissue, the greater the number of the weighting factor. Okay, so if you have this, which is in your data sheet again, so you do not need to know this, you have different weighting factors for different radiations. So X-rays, gamma rays, beta particles are all have a weighting factor of 1 because they're not very ionizing, but slow neutrons have 5, fast neutrons have 10, and alpha particles have 20. Okay, so you never ever need to remember this, but you do need to locate it in your data sheet when you're doing these questions, specifically for equivalent dose. Now, equivalent dose is the biological effect of the different types of incident radiation on a human body. Okay, so you've got your absorbed dose, which is energy over mass. So you've got some sort of energy at targeting some sort of mass, say a tumour. Now, we need to then know how that's going to affect biological harm. So depending on what radiation you use, that's then going to give us an equation of H equals dWr. Okay, so you're basically timesing how damaging that radiation is to someone's body by the weighting factor. Okay, so the absorbed dose times the weighting factor gives you equivalent dose. Now, equivalent dose is measured in sieverts. Okay, SV, sieverts. And absorbed dose is measured in grays, and weighting factor does not have a unit. And remember, to remember it, happy ducks wear rings, but it's also in the equation sheet or data sheet for you for the test and exams. Okay. Now, as we move on from that, it's quite important for us to then talk about equivalent dose rate. Okay? So the equivalent dose rate is basically just a rate of per hour normally. And we don't normally do per minute or per second. It's normally per hour. Sometimes you'd have per year. Basically, depending on what the question asks you, that's the rate that you do. And it's basically this thing called H dot, which is equivalent dose rate. and it's equals to H over T, which is the equivalent dose measured in sieverts, as we've said before, divided by the time in seconds. Now, H dot is sieverts per hour. We've said that's the usual one, but if it asks you to put in something else, like sieverts per day or sieverts per year, you would do that, okay? Just read the question. Now, equivalent dose and background radiations, let's get a little idea of what kind of sievert level we're talking about. And if we were to have background radiation, on average, every year, a citizen in the UK will get exposed to 2.2 millisieverts of background. So milli, remember, is times 10 to the negative 3, so we're talking a very small amount over the year. All right, radiation workers can get 20 millisieverts per year, and an average member of the public should not receive more than 1 millisievert per year. All right, so like if you're an astronaut, you would get much more than that. If you're a pilot, you would get much more than that. And these are very conservative estimates because we're just obviously keeping an eye on people's health. But if you were to get, for example, 1 sievert of radiation, that would be that could cause you to die. Okay, we're talking about millisieverts over a year. That's not a lot of sieverts. Okay, on a daily basis, you're probably getting something like microsieverts. So small amounts mean that you're going to be okay. Okay, so if you see something like 20 sieverts or 50 or 500 sieverts, then you're probably thinking something's not right. Okay, so millisieverts, microsieverts, these are good numbers to look at. Now, sources of background radiation. We've got things like natural radiation, which is like cosmic rays, radon gas from rocks and soil, living things. All of this is natural sources of background radiation. Please remember them. Man-made, things like medical x-rays. If you get an x-ray, that is a form of radiation. Radioactive waste that we obviously take from nuclear reactors, which we'll talk about next week. And a nuclear fallout, which would be very unfortunate to say the least. Yeah, that's probably not going to be a major source of radiation to us because nothing like that's happened in a long time. Now, just to finish off, a couple of wee things and then we're done. You need to know this table, basically. You need to know this table. Just that it comes up in so many different past paper questions. You need to know the ways to reduce equivalent dose. Increasing your distance from the source, decrease time with the source, and use shielding. Super easy stuff. Super easy stuff. Factors that affect biological harm, the type of tissue exposed, the type of radiation, and the absorbed dose. I'm just going through it. You just need to know it. Okay, and then the natural man-made sources of radiation are there as well. So please make sure you know this table, as that will be a good help for you answering questions in the National 5 prelim and exams, no doubt. Okay, right, so that is everything there from me. Well done, National 5. Another week gone by, and we've got another bit of revision under our belts. I hope that has helped. Very well done.